This is problem from slide 12, and it's asking you to draw force vectors on Q1 for these example charges. So I've got a set of 4 charges in a box. Notice that Q1 and Q3 are negative, and Q2 and Q4 are positive. And notice also that all of the charges have a charge of 6 millicoulombs, so 6 times 10 to the minus 3 coulombs. And the length of each of the sides of the box is 0.1 meters, so this is a square. So what we're going to do is we're going to draw the force vectors exerted on charge Q1, so that's on this charge right here. And so if I look at the force on Q1 due to Q2, this arrow is going to point to the right, so I'm on Q1, and my charge is going to have a force exerted on it this way to the right. For Q4, that's this charge right here, this charge is going to exert a force down like that, and this should be the same length, so it should be a little bit longer. And then this charge right here, these are the same sign, they're both negative, so this is going to push the Q1 away, so I'm going to have an arrow that looks like that. So I'm going to have 3 arrows, right? So this arrow, and then this arrow here. Let me just erase this one. And we don't know, we know these 2 arrows are the same, but we really don't know how long this arrow is yet until we do our calculations. So that's part A, and then part B, we need to actually do the calculations. So calculate the net force. And so the way we're going to do that is we're going to use the equation. So for each of these forces, let's call this one Fx, and we'll call this one Fy, and we'll call this one Fd for diagonal. So Fx is equal to KQ, Q, so we'll call this Q, so we'll do this one first. So we'll say KQ2 times Q1 over R squared. And so when we plug in our numbers, we're going to have 9 times 10 to the 9th. I'm not going to do units here. And I'm going to have 6 times 10 to the minus 3 coulombs times 6 times 10 to the minus 3 coulombs all over 0.1 meters cubed. And I find that Fx is equal to, let's see, 32.4 times 10 to the minus 6 newtons. And because the force here depends on Q1 and Q2, this same force here for this force is going to be the same. So I know that Fx is equal to 32.4 times 10. Actually, this is to the 6th, not to the minus 6. I know this is also going to equal my Fy. So, so there I have this force and this force, and now I just need to calculate this force. So I'll call this my Fd is going to equal K Q3 times Q1 all over R squared here is going to be the square root of, so this is my diagonal. And so if I say that this distance away is 0.1 and this distance away is 0.1, this side, and then this diagonal is going to be this squared plus this squared. So I'm going to have 0.1 squared plus 0.1 squared, and so that'll give me this length. So this is equal to 0.1 squared plus 0.1 squared, just using the Pythagorean theorem. So I'm going to have 9 times 10 to the 9th times 6 times 10 to the minus 3rd times 6 times 10 to the minus 3rd all over, let's see, this is going to be, I can factor out the 0.1 squared, so I pull that out and then square root of 2. And so when I actually do that in my calculator, I get 16.2 times 10 to the 6th newtons. Okay, so now what I need to do, now that I have this hypotenuse here, I need to find the x component and the y component. So let's do Fd sub x, and looking at that, this is a square, so my angle is going to be 45 degrees. So this angle is 45 degrees. Then if I'm trying to find this component of this is adjacent, so this is going to be cosine. So this is going to be Fd, the diagonal times cosine of 45. And that's equal to 8.5 times 10 to the 5th newtons. And because this is 45, I'm going to have FDY is equal to FD sine 45. And that's also equal to 8.5 times 10 to the 5th newtons. And so now I have this length, and this is pointing this way, so it's pointing to the left, and this length, and that's pointing up. Right? And so if I look back at my fx and fy, this is 32.4 times 10 to the 6th, this arrow, and this arrow is only 8.5 times 10 to the 5th, so I know my net is going to be to the right, and the same thing for down. It's going to be down. So I'm just going to have a shorter arrow going this way and a shorter arrow going this way. So I'm subtracting this x component from this x component. I'm subtracting this y component from this y component. So let's see, I'll turn the page here. So I'm going to have fx net is equal to, let's see, 32.4 times 10 to the 6th newtons minus 8.5 times 10 to the 5th newtons, and that equals 23, well, let's say 24 times 10 to the 5th newtons. And the same thing with y, times 10 to the 5th newtons. Right, and so now I have this new arrow pointing this way. Right, I came up with an x component, that's my 24 times 10 to the 5th. My y component, that's my 24 times 10 to the 5th. So my f net is equal to the square root of fx net squared plus fy net squared. And so when I plug that in, I get f net equals 24 times 10 to the 5th newtons squared plus 24 times 10 to the 5th newtons squared. And so I can factor that, and that would be 24 times 10 to the 5th newtons times the square root of 2. And when I do that math, I'm going to get f net is equal to 34 times 10 to the 5th newtons. And so that's my, and that is my net force going this way, and I know theta is equal to 45 degrees, so this is my theta. So I can either say that my direction, so theta is equal to a negative 45 degrees, or theta is equal to 360 minus 45, which is going to be 315.